Okay, we'll go ahead and get started. Good morning, everybody. I'd like to welcome you to the webinar series on managing drought in the Southern Plains. I'm Mark Schaefer with the Oklahoma Climate Survey and Southern Climate Impacts Planning Program, and I will be the moderator for today's webinar. We will be joined by Brian Fuchs from the National Drought Mitigation Center, Mike Crimmins from Arizona Cooperative Extension and Climate Assessment for the Southwest, and John Nielsen Gammon, Texas State Climatologist. Margaret Boone, SCIP Program Manager, is managing the webinar. We are switching off into some different software this time. We're using Adobe Connect and streaming the audio, so hopefully everybody will be able to hear us. If you notice any problems in hearing us, feel free to dial in at the number on the screen or the number that was sent with the registration email. I would like to remind anyone who is calling in to please mute your phones, either using the mute button or *6. In addition to today's presenters, we have several state climatologists on the line, including Mike Borengasser from Arkansas, Dave Dubois from New Mexico, Pat Ganan from Missouri, and Renee McPherson from Oklahoma. I would also like to recognize the support of those who made this webinar series possible. Chad McNutt with the National Integrated Drought Information System, or NIDIS, David Brown with the NOAA Regional Climate Services Director for the Southern Region, and Mike Hayes with the National Drought Mitigation Center. I'd like to briefly recap the goals of the seminar series. We planned these in order to improve communication across our region to help those agencies and organizations that are managing aspects of the drought. We want to ensure that the information presented is timely and relevant. Our presenters will include a combination of scientists, state climatologists, and resource managers. For example, when we do a webinar on water resources, one of the presenters will be a manager of a water district or a state water resources agency. If you have expertise in a particular area and would like to be a presenter or would like to recommend others we should ask, please contact us. I would like to also underscore the importance of reporting impacts. Brian will speak to this a bit more, but we have many recent examples where reports from county officials have been important considerations in creating the weekly drought monitor, which in turn has implications for federal assistance programs. Please encourage participation by your state and local officials through the Drought Impacts Reporter or by contacting your state climatologist. Our partners have developed a tentative list of topics. These are grouped into two general categories. One set focused on specific sectors or activities, and the other set focused on resources and monitoring tools. We plan to alternate between these sets of topics. You should see a poll on your screen right now that asks which of the topics from this list you would like to see next. Please cast your vote now. If you would like to suggest additional topics, you may do so through typing in the dialog box on your screen. We will incorporate these suggestions into future polls. Lastly, these webinars are an ongoing series that will occur on the second and fourth Thursdays of each month. Our next webinar will be October 27th. Each webinar will include an update from the Drought Monitor authors and state climatologists. Each will have a discussion topic based on the topics of greatest interest as indicated by the poll, subject to the availability of presenters. You may ask questions or make comments at any time through typing in your dialog box. Each webinar will be recorded and a brief PDF summary will be produced and posted on the NIDIS portal, drought.gov, in the Southern Plains section. We will put up a list of resources, including these links again at the end of the presentation. We'll now turn it to our first presenter, Brian Fuchs from the National Drought Mitigation Center. He will be followed by Mike Crimmins with Arizona Cooperative Extension and CLIMAS, and then Texas State Climatologist John Nielsen Gammon. So, Brian?
Good morning, everyone, and thank you for the introduction. Again, my name is Brian Fuchs. I'm a faculty member and a climatologist here at the National Drought Mitigation Center, which is housed at the University of Nebraska in Lincoln, Nebraska. And I'm also one of the Drought Monitor authors. And what I will be discussing with these slides today is an update of current conditions with the U.S. Drought Monitor released this morning, get into some of the outlook, and then finishing off with a quick overview of a new and updated drought impact reporting tool that is being developed and housed here at the National Drought Mitigation Center. So next slide. Here's today's U.S. Drought Monitor. And I know as we went into the weekend, we were really looking at this rain event developing through the central and southern plains and how that was going to impact the region. Fortunately, the system did do what we'd wanted, and that was stay together and develop as it went east. And we did see some substantial rains through the southern plains, most of which had not been seen any events similar to this in the last year. We were able to show some slight improvement with this recent release of the drought monitor, especially in portions of Oklahoma and Texas that did record the most precipitation with this event. Many of the other regions across the country were left basically unchanged this week, with some improvements through the Midwest as well as through the Florida Peninsula. To go to the next slide with more of a regional view, you can see that through the southern region of the United States, that the current conditions, which are stated in the summary table off to the left of the graphic, and you can see that there was a slight change through most of the conditions, especially some improvement of D4 and D3. But what I'll really point out is looking at the current D2 to D4 from last week to this week, those numbers were really unchanged. And that was showing that with the drought that we're experiencing in this region, even the one rain event with the improvement being shown on the drought monitor, it was really a single category improvement for most locations. And that makes sense that one rain event with as dry as it's been in that region is really not going to turn fortunes around that rapidly. Realistically, the impact of that rain is going to be on the short-term side, where we see some agricultural conditions improve slightly as we start to get some moisture into that soil profile again. Also, with this rain event over the weekend in the areas that did see the most rain, it will do a lot to help suppress some of the fire danger that we've seen on and off through the last several months. Going to the next slide, we can see that conditions to the west, especially focusing on Arizona, New Mexico, and Colorado, were basically similar to what we saw in the southern U.S., that there were some improvements. Most of this area did not see the same rains that went further to the east, and so we still see drought, especially in New Mexico and into southern Arizona, really gripping the region, and not much improvement this week overall. Going to the next slide. With the outlook that we're seeing, we can see the remnants of the system that came through over the weekend in the first part of this week slowly moving off to the east. And so pretty much east of the Mississippi River Valley is where we're seeing the precipitation chances over the next 5 days. And on the U.S. Drought Monitor map, we're really seeing that the areas that are still being impacted by drought, not seeing a tremendous amount of precipitation as it's falling further to the north through the Great Lakes and the Ohio River Valley. Looking at the graphic in the lower right-hand side, this is the 5-day temperature outlook, looking at the departure of normal for maximum temperatures. And you can see a lot of red on this map. That's seeing that temperatures over the next 5 days or so for almost the entire country outside the far northern reaches are going to be above normal. And again, through the southern plains and southwest, we're seeing those greatest departures of anywhere from 6 to 9 degrees above normal. So the heat that has been experienced through that part of the country is still maintaining itself again as we go into fall. As we go to the next slide, on the 8 to 14 day outlook, we can really see in the upper left-hand corner the temperature probabilities. And what really stands out is the warm temperatures all the way from Alaska down through much of the western U.S. and even into South Texas. And those areas, again, that we're seeing below normal, that's really where we're experiencing the most rain. And it's going to hinder those temperatures as that cool air that has passed through the central U.S. moves to the east, and we still see that trough of cool air coming down into that region. The lower right-hand side, again, is the precipitation probabilities over the next 8 to 14 days. And along with those warm temperatures through the central Rockies and into the southern plains and southern Mississippi River Valley, we see the best chances of below normal precipitation. and the remnants of the storm system moving off to the east is showing the above or better than normal chances over the eastern quarter of the country into Florida. And so what this is saying that for the region of interest in the southern plains, New Mexico, Arizona, temperatures are going to bounce right back up, and the chances of above normal precipitation are quite low going into the next week to 2 weeks. On the next slide, we have a summary slide for both the month of October as well as October through December, again coming from the Climate Prediction Center. And starting up on the top two images of this frame, looking at October, we continue to see the temperature outlook below normal through the western U.S., equal chances through much of the eastern Rockies and into the southern plains, and above normal temperatures pretty much from the plains all the way through to the east. Along with that, they're still showing that there's some remnants of above normal precipitation through this time. What I will note on this graphic, it was made on September 30th, and the update for it should be coming along, but a lot of the above normal precipitation shown on this graphic has been associated with the system that we've seen already this month that's continuing to move to the east. As we look for more of the seasonal outlook here, October through December, again, we're seeing the classic La Nina setup of above normal temperatures and below normal precipitation through the southern tier of the U.S., and we continue to see that become stronger as we move further into the fall season, and pretty much expect this to continue through at least the early part of winter. And I know Mike will be discussing this further on his slide, so I'll leave that alone. Going to the next slide, this is the seasonal drought outlook that's put together by the Climate Prediction Center. And what they're doing is they're taking the U.S. Drought Monitor from last week. As you can see, the release date on this is October 6th, and it comes out about every 2 weeks. But what they're doing is taking the drought areas from the U.S. Drought Monitor and along with their forecast tools, looking at areas for improvement to the drought conditions, persistence of the drought conditions, or actual improvements to it. And we see this area from Kansas through the Oklahoma and Texas panhandles for some improvement. And a lot of the skill with this product is on the shorter term time scales, even though it does go out through December. But that some improvement area was where the forecasted areas for the rains that were associated with the system over the weekend were projected to be. They were offset a little bit further to the east, and the band was not as wide as what the Climate Prediction Center was hoping for with the release of this product back on the 6th, so last week. But we did see some improvement in this area, but the main overall picture you can see from this graphic is the continuance of the drought through the southern U.S. There are some areas that as systems do roll through and we do get some precipitation from them, there are chances for some improvement. And to make note on this product, improvement on the drought outlook is at least a 1 category change to the U.S. Drought Monitor. So for a lot of these regions that are in D3, D4 drought, even a 1 category change is still showing them in fairly significant drought situations. I'll push you to look at this project again here next week as it does get updated. And that concludes the overview of the Drought Monitor and the short-term outlook. And again, this week, I know on the last call we had a featured product from the NDMC and the U.S. Drought Monitor. And the product I'm going to highlight in this call is, did everyone know that there's a new and improved drought impact reporter available from the National Drought Mitigation Center? And I think if you click the slide one more time, you will get the URL for this. It's at droughtreporter.unl.edu. And what this is a drought impacts reporting tool that we not only take information on drought-related impacts, but also drought-related reports from areas, and we put them into a database that is searchable and gives people an idea of, from each drought event, that there are baseline impacts that can be recognized for a region, and many of these impacts have never been saved in such a way, and so this is how the Drought Impact Reporter tool evolved, and we've just had a new release, which on the next slide I'll show you the front page of. And so for those that have used the tool, you can see that it is strikingly different in look and feel compared to what we used to have with the Drought Impact Reporter. You come into a frame here of the entire country that's color-coded based on the number of impacts, and the default is over the last 30 days. I have a red circle highlighting that we are indeed separating what drought impacts are and what drought reports are. And just a quick idea of what that means is a drought impact is something that we can show a loss related to drought, specifically that an area is suffering from, where a drought report is where we have a user out there that's recognizing it's dry, they're telling us that it's dry, but they don't necessarily have discernible impact that can be related to that dryness. But we still like to capture those because it does give a good picture of the region of there is dryness, these are the types of things happening, and some of them are drought-related impacts. You can see also down towards the bottom part of the frame, we have different categories that these impacts are put into. Agriculture, energy, plants and wildlife, society and public health, water supply and quality, business and industry, fire, relief response, restrictions, and tourism and recreation. And all of the impacts and reports that we get are put into these categories. If you go to the next slide, I highlighted Oklahoma here, in particular Carter County down in the south central part of the state. And you can see that the total number of impacts and the statewide impacts that are being reported, the categories they fall into. And from this frame, you can click on that green box where it says impact list, and you will actually get the information related to these impacts being shown. In the upper right-hand side, I have a circle around where it says overlays. And one of the overlays is the current drought monitor that you can put on here, as well as hydrologic units, climate divisions, congressional districts, RMA regions. So you can take this information for any region that you're interested in and put these overlays on. And if you go to the next frame, you can see what the Oklahoma situation would look like with the drought monitor map being shown in behind it. Again, I moved to a different county. I moved to Jackson County now in the southwestern part of the state, but you can see this area is well entrenched in D4, the types of impacts that they've seen over the last 30 days. And you can get an idea how this can help the U.S. Drought Monitor authors. We really want the Drought Impact Reporter tool to be a venue where the general public or users who are concerned can come in and relay the information for their area. And a lot of times we've used this tool as a way, as a conduit for regions to also discuss how they feel that they should be represented on the Drought Monitor. And a lot of times we'll have people come in and relay information about crop losses or dryness in their area. And sometimes there is a disconnect between the data that we're using to put together the drought monitor and the conditions on the ground. And so we can use this information to fill in some of those areas where the data may be showing a wet signal, but we're seeing all sorts of drought reports and impacts coming from an area, and we can dig down as to why we're seeing that, and also have people relay some of that loss information. So we really do encourage users to come in here and contribute to this database and use it, because in the end it is going to help with a better drought monitor depiction for their region, which we all know is important, as Mark mentioned, with the use of the drought monitor and some relief programs by different federal agencies. So I think that is my last slide, and I think we're waiting to the end for questions, Mark.
Yes, if people want to go ahead, if there's questions, you can go ahead and type them in your box, and we'll get to those at the end. So we'll now move on to Mike Crimmins is going to talk about the what La Nina is.
Good morning, everyone. This is Mike Crimmins from the University of Arizona. I'm an extension climatologist with climate assessment for the Southwest in Arizona Cooperative Extension. Next slide, please. So I think this is really basic, but I think it's a really good first place to start, just to make sure we're all on the same page as far as concepts and mechanisms as we go forward here. And what I'm going to try to do in about 10 slides is give you a snapshot of some of the basic fundamental concepts of how La Nina works. And I think that the reason that this topic possibly came up is spend a lot of time talking about this as meteorologists and climatologists. It shows up in the media quite a bit. And you're hearing that the Pacific Ocean has consequences for the central United States, and it's not completely intuitive in exactly how that works. So we start off with some of these fundamentals of just Weather 101, and I think everybody knows this, but if we start off with things that you look at on an everyday basis as far as looking at weather maps, we have things like low pressure systems. We're looking at, when I'm talking about surface low pressure systems particularly, rising air, counterclockwise circulation, and that rising air provides the lift necessary to produce precipitation. So in meteorological and climatological terms, we're looking for things that produce lift in the atmosphere to produce precipitation. Then another thing that you'll hear us talk quite a bit about is we assess about the position of the jet stream, both in a diagnostic way, where it is right now, and then looking at forecasts out into the future, both in the 7 to 10 day forecasts, and if we can do a good job looking out at the large scale circulation patterns into the future, can give us a feel of where these low pressure systems are potentially being steered and forming. And when I talk about the jet stream, I'm in particular talking about the high speed stream of wind that forms in response to a surface temperature gradient at about 30,000 feet. And really it provides that energy. It helps reinforce surface features, both high and low pressure systems, and really serves as a mechanism to steer storms in the westerlies. And that's another thing I'm going to show you a little bit about. That in the northern hemisphere, the jet streams are out of the west, so they're coming from the west, moving to the east. We call them the westerlies. And then high pressure systems, giving you that in Arizona, anyways, postcard weather, always under the influence of high pressure systems. That sinking air, warming air, and then sinking air is counter to the mechanism you need to actually lift and produce precipitation. Clockwise circulation, and so that's associated with dry conditions. And on a classic weather map, L's, the low pressure systems are red, and my H there should be blue. I think we had a little bit of a conversion there. Next slide, please. Okay, so this is obviously the planet, and what I wanted to do is to have you start thinking about this idealized global circulation. This is usually where I sort of start off when we talk about El Nino and La Nina. And you have to think of the atmosphere as a three-dimensional fluid that's flowing off in many directions. And if we think about the function of weather, all function of weather is to move energy that accumulates in a surplus at the equator, moving it to the poles. And it has to do this in a fairly complicated way when we're talking about the atmosphere, because the planet is spinning. So this movement of energy from the equator to the poles breaks out into small eddies, or large eddies, relatively speaking, that then show up into these surface high and low pressure systems, but they're also stacked through the atmosphere, and we have interesting cells that break out. So the thing that, I don't have a pointer here, but I'm going to try to use my geography as best I can here, and have you take a look at 30 degrees north there. We have something called the subtropical highs, and at the equator, we have what we call the intertropical convergence zone. So if you look at these little cells of circulation, we have one called the Hadley cell, where there's rising air at the equator, and it reaches the top of the troposphere and then flows out to the north and then sinks right about that 30 degrees. And sinking air is related to those subtropical highs. We have another cell that's just north of that called the Ferrel cell, which is the connection and the movement of energy from the cold polar air towards the south. So it's sort of this mixing out of energy from north to south. The surface flows that I want you to think about here, though, is that along the equator, the winds are out of the east, moving towards the west, and then north of the subtropical high, the winds are out of the west. So you can think about that there is a persistent easterly flow at the equator and a persistent westerly flow north of that. And can you hit the next slide, please? My little features fly up there. We have surface high pressure, where we have that sinking air, that what goes up at the equator comes down about the subtropics, sinks there, or subtropical highs. And then north of that, we have this division between the warm air of the subtropics and the cold air of the polar front. That's where the jet stream will form in response to that temperature gradient, and we're looking for low pressure systems to ride along that frontal feature. Next slide, please. Okay, so that previous slide is very, very idealized. It's much more complicated than that, but conceptually has most of the main features we're looking for. So this is, again, idealized, but a little bit more complicated and a little bit more realistic, is that these frontal features turn into jet streams. We have two of them shown here. The mid-latitude jet is that one, the division between the cold polar air and then subtropical air, and then another jet stream is subtropical jet, forming in another temperature gradient that forms in the subtropics. These are idealized. They come together at some point. They move north and south in the northern hemisphere, and they wiggle around. And if you can hit the next slide, please. The wiggles are really what we're looking for in forecasting and in diagnosing what's going on from a precipitation standpoint. When the jet stream has real strong wiggles or waves in it, technical term, waves in it that go from north to south, that will give us lots of energy to work with and mixing out that energy, and then that will reinforce surface high and low pressure systems. The jet stream can also get stuck in these patterns, which is really where we segue into the idea of La Nina. So when the jet stream dips south, that's a typically low pressure. Some features form in that, and then when it moves to the north, we have high pressure. So the L there, surface low, and then that little, what we call ridge there, is where that H is. Next slide, please. Okay, so now making the link from this idealized circulation to La Nina, we first have to think about what actually happens in the equatorial region. So if I go back to our idealized graphic here, you can see that easterly flow and those arrows converging along the equator, that area is getting baked with sun, most of the solar energy throughout the year, so it's accumulating a lot of energy. But if you can imagine then too that persistent easterly wind moving along the Pacific Ocean, there's frictional coupling, and there's an actual ocean atmosphere coupling that goes on across the Pacific. So that frictional coupling is moving that warm water off to the west very, very persistently. And if it's doing that, water has to flow back in to replace the water that's moving off to the west. And so what actually happens is that it induces upwelling along the South American coast. And so that water that's coming up from deep is cool. So instead of just having a nice swath of warm water from the South American coast all the way across the Pacific at the equator, you have this pattern where the upwelling brings cooler water to the surface. The warm water then is concentrated in the western Pacific, and you get a gradient across the Pacific that helps reinforce itself. The warm water in the western Pacific is where convection, it's warm enough that it actually can release the energy and water vapor in the atmosphere and produce this convection. And so every flow in the atmosphere is closed. So whenever one thing is going one direction, there has to be some kind of return flow. You can imagine then that we've got this rising air at the equator, it's flowing out north and south in this Hadley cell circulation. We also have along the equator winds flowing out of the east, but at the upper levels flowing out of the west, and that's called the Walker circulation. You can see the arrows in this lower left figure down here in the slide here, showing that other part of the circulation. So you can imagine then that what happens in the Pacific ends up resonating and flowing out into the rest of the northern hemisphere, which then brings us to this idea of, well, how can it affect weather downstream from the Pacific Ocean? Okay, next slide, please. So La Nina is an interesting phenomenon. That previous slide showed you that normal pattern, cool in the eastern Pacific, warm in the western Pacific. When the easterlies become stronger than normal, it will actually shove that warmer water further to the west. That area of convection gets shunted further to the west. And then colder water then is driven up to the surface in a stronger upwelling in the eastern Pacific. So you have colder water in the eastern Pacific, and then warmer water shunted further and further west. The Walker circulation responds to that, and then that has implications for the jet stream in the northern hemisphere. And I'm primarily talking about impacts in the wintertime. That's when this is strongest, because our weather systems that cross the continental United States are primarily driven by the mid-latitude jet stream. Okay, next slide, please. Okay, so going back to last winter, we had stronger than average easterlies form last summer and started to drive this sort of reinforcing pattern of more convection in the western Pacific, drawing in stronger easterlies and feedback, basically, helping to reinforce this La Nina pattern. And so this graphic in the top here is the departure from average sea surface temperatures across the equatorial Pacific. So you see Australia down in the lower left, you see Mexico and part of the southern U.S., and then South America on the right side of the graphic. That blue area is sea surface temperatures that are below the average temperatures that you'd expect to see in the November through January time period. So this is the signature of the La Nina from last winter. And one of the ways we can keep track of whether we're in La Nina or El Nino or neutral when things are average across the Pacific is by simply measuring the temperature departures in parts of the Pacific. So the graphic just below that on the lower right part of the graphic is some boxes where we just take simple temperature measurements of sea surface temperature and then plot them out in graphs. So one in particular you may hear people talk about is Nino 3.4 box. And that translating into a time series graph is in the lower right here. Sorry, the graph was in the lower left, the boxes were in the lower left. The time series graph is in the lower right. Shows you from about 1982 till last winter, red showing us swinging into where that water in that area is warmer than average, showing us El Nino conditions, the blues indicating in the deeper the blue, the strength of the La Nina. So you can see some of the bigger events of the last 30 years showing up here, in particular La Nina events, the blue spike sticking down, and then there's our previous 2010, 2011 La Nina right at the far right-hand part of the graphic. Okay, next slide, please. Okay, so this idea then that we have a change in strengthening of the easterlies, we have then a disruption at the upper levels of the atmosphere where the jet stream occurs, changes in the wind speeds, basically, that happen in the upper levels of the jet stream, and that return flow at the upper levels of the atmosphere into the rest of the northern hemisphere. That then has implications for our mid-latitude jet stream that's coming across the Pacific and getting ready to break into the continental U.S. and bring some weather to us. And under neutral conditions, the jet stream isn't really being perturbed by the Pacific, so it can swing around, can have a lot of waves, and it can be kind of up to natural variability at that point. But when we have La Nina conditions, that disruption can stick the jet stream and deflect the jet stream to the north, in particular both the polar and the subtropical jet, sometimes kind of converging them into one consistent jet stream, and steer the storms up to the Pacific Northwest, and then merging with the polar front, diving through the Midwest in that gradient of cold polar air that's usually cooling up there, and stick the jet stream in this position where the storms enter through the Pacific Northwest, drop through the upper Midwest, and then take off into the Atlantic off the East Coast. That sticking of the jet stream leaves the southern tier states with little activity. And it's an easy thing to happen because we don't often have, we don't have as much possibility for real good storm activity, especially in the Southwest in the wintertime, as the Pacific Northwest. Okay, next slide, please. So if we take a look at what we would expect to see the jet stream to do during January, and I'm just going to zoom in on 1 month in particular because I think it kind of isolates the pattern that we saw last year, best of the whole wintertime. And John's going to do a better job of really isolating how that La Nina event transpired through the rest of the spring and really brought the deep drought conditions. But I'm just going to zoom in on January in particular. So this is what we'd expect to see on average. The deep yellow and red colors are where the jet stream is strongest and most persistent. So far western Pacific, it has a very persistent speed exit region off of the Asian continent, and then this smearing out along of blues along the Pacific West Coast means that the jet stream often will have waves north and south, so it doesn't necessarily get stuck in any particular pattern, and that's what we normally see on a normal January. And the arrows kind of tell that story too. They don't all point in one direction, either north or south. They're kind of even out there, and that's what we'd expect to see in a normal January. Next slide, please. Okay, and then that's actually I'm trying to show here with the two little weird green arrows there, showing that the jet stream can loop north or south, bringing storms to the whole entire west coast and the rest of the central part of the country. Okay, next slide, please. This is what actually happened last January. It looks quite a bit different than the normal jet stream pattern. If you notice here that the jet stream colors, instead of being that nice even blue along the west coast, are, yellow, red, green in a stuck pattern. And if you go back to that previous graphic I showed you of what a La Nina pattern looks like, they look pretty similar. And so that ridging pattern, or having that high pressure in the East Pacific, really anchored itself down, deflected the storm activity up through the Pacific Northwest. And so it drops through the upper Midwest and really leaves a lot of the South Central and Southwest out of the storm activity. January wasn't a perfect example because Texas and some of the other Southeast states did pretty well off of some subtropical jet activity. But that shifted later in the season, and you saw more of a canonical La Nina pattern. Okay, next slide, please. There's the little jet stream pattern to isolate the features that I wanted to show. Okay, next slide. So just to quickly finish up, if you think back to where the jet stream was, this is, John actually stuck this in here. This is the classic La Nina pattern here of the northern, northwest and northern tier states do best in having persistent jet stream activity, so basically dragging those storms across, and you get wet anomalies, and then when you're south of that and under the influence of high pressure, you break on the other side of that and have dry conditions. So it really is about this persistent sticking of the jet stream that La Nina does very, very well and brings very consistent impacts to the continental U.S. Next slide, please. And then the temperature patterns are quite similar too. If you're on the southern side of the jet stream, you're going to be warmer than average, and if you're breaking with average precipitation, above average precipitation, you're going to have closer to average temperatures, if not below average temperatures if you're on the north side of that jet stream. Next slide. That's all I got.
All right, so I'll bring things into the present and future now, talking not just about El Nino, but also some of the longer-term patterns that affect the weather across the Southern Plains. Next slide, please. So the box is the Nino 3.4 region that you just heard about, and the map on top is the current sea surface temperature pattern, and you can see a tongue of cold water running right along the equator in the central Pacific. It's normally somewhat cool there, but the map on the bottom shows that the temperatures are actually below normal. The shading is at least half a degree below normal, so we see most of that box is below normal, as is indeed most of the tropical Pacific. Next slide, please. This is a graph of that index over the past year. Last year at this time, we were running 1.5 degrees below normal. We were in the middle of a moderate to strong La Nina, and that persisted into February, and then temperatures started to moderate in the tropical Pacific. It ended officially in early May when temperatures crossed the threshold of half a degree below normal. And things were looking good, but oftentimes when you have a strong La Nina, you have another La Nina on its heels, and that indeed seems to be what's happening. We crossed back over the threshold in early August, and if it lasts for another month, we're going to have an official new La Nina event. Right now it's called La Nina conditions, but the Climate Prediction Center says there's a very high chance of La Nina persisting through the winter time. So you heard about the typical conditions in the United States under La Nina, and you recall and saw what we had last year. And so you might imagine this year is looking to be dry as well. I won't say similarly dry because last year was unusual even for a La Nina. It was for the southern United States, except for California, perhaps the driest La Nina that we recorded. So odds are this one will be better, but still, unfortunately, it means a second year of drought for places that are already in severe to exceptional drought. So that makes 2 years of drought. Let's look at how long this drought might actually last. And the way we deal with this, there are a couple of ways. Like with El Nino, La Nina, we can look at past records, but when we're talking about temperature patterns that change on a time scale of decades in the Pacific and Atlantic, there hasn't been a lot of a track record for us to tell what typically goes on. The other tool is climate models, and it's a neat technique they use. This was a coordinated set of experiments by multiple researchers, including several federal agencies that I'm going to just briefly touch on. Two steps, basically. First step is figure out the typical patterns in which the Pacific and Atlantic and Indian Oceans change in time. You know, when part of it gets warm, does another part get cold, and do they move in sync? And you find these synchronous patterns that show up over the past century. The top one is basically most of the oceans being either warmer or colder at the same time. And the time series on the right shows that it's gone from colder to warmer. So this is basically the long-term warming trend that we're familiar with around the globe. The second pattern looks a lot like El Nino and La Nina. You've got largest changes in the tropical Pacific Ocean with cooler temperatures to the north and south. And the time series of that shows that compared to the first one, there's a whole lot of change from year to year. The line's going up and down rapidly. But you can also see there's a little bit of a long-term signal there as well. It was kind of high during the 30s and early 40s, kind of low during the 50s through 70s, kind of high during the 80s and 90s. And that longer-term signal is something we call the Pacific Decadal Oscillation, or PDO. And when it's negative, things are like La Nina conditions in North America. We can tell this not just from past history, but the second part of this experiment, when you run a climate model with this particular temperature anomaly pattern in the oceans and see what the atmosphere does, and run it for like 30, 40 years, so you average out the vagaries of weather, you do indeed get consistently dry conditions in the south central United States. So observations and models are saying the same thing there. The last pattern is mainly in the Atlantic. You might call that the Atlantic Decadal Oscillation, but unfortunately, no, we're not that simple. It's the Atlantic Multi-Decadal Oscillation, AMO. And you can see it's not quite as noisy as the Pacific pattern, but it also does go up and down on a multi-decade timescale. You may not have heard of this by name, but you've heard of its consequences. We've had active hurricane seasons almost every year since 1995. That's been tied to the warm Atlantic. Well, that's this index measuring that. And you can see on the graph since 1995, it's been mostly positive, which means the Atlantic has been mostly warm. Now, observations and some, but not all of the models indicate that when we have a warm Atlantic, we also tend to have dry conditions in the southern plains. So the bad news occurs when the tropical Pacific is cold and the North Atlantic is warm. Next slide. Here's a graph of those time series over time. I've highlighted the two periods in the record when those two signals have lined up, cold tropical Pacific and warm Atlantic. And the last time was in the 1950s and early 60s, which of course includes the major 1950s drought, the worst drought for the southern plains as a whole, certainly the worst drought in Texas, although from Oklahoma north, the Dust Bowl gives it a pretty good run for its money. So we had a long-term drought during that period, as well as a couple of short-term droughts in the 60s. Then it's been back since about the year 2000, and we've seen several short-term droughts interspersed by wet years in this interval as well. Next slide. So to put this together, as we go down this slide, it becomes increasingly less certain and more dependent upon recent research results. But we almost certainly have a returning La Nina, which means that across the southern plains as a whole, a drought is likely to continue. It's most likely the farther south you go, because that's where the correlation with La Nina is strongest. But we're also in a period since about the year 2000 of enhanced drought susceptibility because of the long-term patterns of temperatures in our oceans that surround our continent. And that period is going to last, well, we don't know how long it will last. Based on past track record, it tends to be in a particular phase for a couple decades, so maybe it'll be gone in 2 or 3 years. Maybe, if we're unlucky, last another 15 years. So The only thing I can say to improve upon that is that in the future we'll actually probably be able to actually forecast this, because we're just starting to run computer models that simulate what's going on within the ocean. So that much like we have weather forecasts today, we might have ocean forecasts in the future. But this period of drought susceptibility, we've had dry years interspersed with very wet years. And there's really no way to tell whether that's the same sort of thing we'll see going forward, whether this will be just a 2-year drought, or whether we might not have a nice strong El Nino event to break things up, and we might actually end up with several years of drought. Certainly the pattern is set up to allow that to happen, and we know it's happened in the past, not just the 50s, but also based on freezing records several times during the past millennium. So that's sort of the worst case scenario. Next slide. I think that might be all I have. So I'll turn it back over to Mark.
Right. I'd like to thank our presenters and everybody who's joined us. I realize that this has been a bit longer than we typically go, but as you can see, this is a pretty complex topic, and we wanted to convey how things far away can affect us. So I hope that message has come through. We'll get to any questions, but first of all, I'd like to ask if any of our state climatologists have any comments or updates they would like to. I think Dave from New Mexico and Pat Ganan from Missouri have indicated they might have something. So Dave, are you on the phone?
Yeah. Hi, this is Dave Dubois, the Mexico State climatologist, and I just wanted to just give a real short briefing on compared to last time we met. So there's been a little bit of relief in these as a whole for New Mexico, only in the middle, the upper Rio Grande Valley and the northwest corner. But the areas that have the biggest impacts of drought are continuing to suffer. I was just looking at some the climate data up until yesterday, and I just wanted to give a couple little tidbits of conditions. And I was looking at some of the stations in the very far southeast corner, near closer to Texas, and for instance, like Hobbs and Jowl. In terms of year to date, they're still they haven't really got much. Actually no improvement. They've had just a little bit, and they still are around single-digit % of normal for year to date precip, and then another up by Roswell at the Bitter Lakes. That's wildlife refuge are about 16% of normal. So that the southeast still part of New Mexico still is suffering under our drought, and there's been a few areas where there's been some relief in the middle part of New Mexico, where they've had last week they had some rains in the 1-inch range, a little above, that were more than the October normals for that. But just looking at the forecast from NCEP, that may be only the only thing that they may be getting for a while. So I just wanted to give that as a few areas, maybe one category improvements in those areas that I talked about who had some rain. But other than that, there's been no improvement. So back to you.
Wish we had better news there. And I think it's Pat on the phone.
Yeah, Mark, can you hear me?
Yep.
Okay. Thanks, Mark. I just want to briefly talk about a situation we had here take place in Missouri this past summer, which was a situation I don't recollect happening since the inception of the Drought Monitor map. And that was one of high temperatures that we experienced, exceptionally high temperatures this summer in southwestern Missouri, where the drought was just as much as temperature-driven as it was by the lack of precipitation. And it has become fairly disconcerting. It seems like the drought situation in southwestern Missouri was put on fast forward, and it had taken a significant amount of time, I think, to perhaps accurately reflect the severe situation that had emerged rapidly across southwestern Missouri, not only because of the high temperatures, lack of precip, but we also have some very shallow soils in southwestern Missouri. And so despite what antecedent conditions might be, it can be a 2 to 3 week period before, if you have no precip, we slip into an agricultural drought across that area. And I think when I visit or look at some of the information that comes across in regard to the objective indices on defining a drought across the U.S., a lot of them are precipitation driven, and it would be really nice, perhaps, especially during the growing season when you have some unusually high temperatures like we've seen this past summer across parts of the central U.S., that we pay very close attention to a drought situation that could rapidly emerge like we saw in southwestern Missouri. And because of that, we have seen some producers who have been frustrated by what they see on the drought monitor map this past summer and what actually was going on. And so I just wanted to put that on the radar because I think it's a very important consideration with these high evapotranspiration rates that take place. We don't have any ET monitoring that occurs throughout the state of Missouri. I know Oklahoma has a really good network of ET monitoring, but we do have some Class A pans, evaporation pans, and indeed, we have one pan in southwestern Missouri that did indicate some of the highest evaporation rates since 1984, so almost 3 decades, and yet temperatures were the hottest since 1980. And so it really was a wake-up call for me, and hopefully for people involved with generating the drought monitor map to pay very close attention to high temperatures that occur during the growing season and the impact of how fast it can really bring a drought across certain parts of the United States.
Hey, Mark, this is Brian Fuchs, and I will respond to Pat real quick if I have time.
Go ahead, Brian.
Pat, you bring up a great point, and it is something that retrospectively we looked back on, and we can see that the temperatures this summer, especially in certain parts of the country, Arkansas, Missouri, and even into parts of the southeast, we were seeing that temperatures were playing a big part in the drought development in that region, and not only was precipitation or lack of precipitation a factor, but temperature was indeed the driving force. There are some drought indices that we are developing, or that have been developed, that we're working on getting out to the public here at the National Drought Mitigation Center. One of them is some work that it's similar to the SPI, but it also includes a temperature component, the SPEI drought index, and we're looking at getting that up and running with some similar type of output that we have currently for the SPI. And I think that by itself, just having some more temperature indicators that include temperature data is going to help. Another product here at the Drought Mitigation Center that we're looking at for picking up these flash type of drought events is the VegDry product, and looking at that vegetation response, because it does take that remotely sensed data along with climatological data inputs to give conditions. And it's one of those case studies that we're going to have to go back and look at the performance of some of these to get an idea, are they adequate in picking up these signals? Again, like you said, some of these really caught some of us off guard.
Thanks. And I'd also like to underscore, going back to the reporting, because a case I've worked with Mike Borengasser in Arkansas, seen similar effects as what Pat described in southwest Missouri. And it was the reports that we were getting from the people in the county's FSA offices, water or irrigation districts, that caused us to focus our attention and really start taking apart the different indices that we had to try to figure out what was going on. And there's a large area for people to look at. The drought monitors are looking at, drought monitor authors are looking at the whole country. The state climatologists are looking at the whole state. So when you send in a report, it helps focus our attention on an area if something's not matching up right, that we can then do a little bit of investigation. Okay, I see we have another question. Travis Miller, 2001 also had unprecedented wind runs go with the high temperatures. Should this be a part of the model? I'll kind of toss it out there to the people on this call. I just kind of mentioned some of the what they call evapotranspiration models or evaporation models do have winds as a variable, but any other comments out there? No? Okay, well, I know that what we saw earlier this year is from the Oklahoma mesonet stations, especially across western Oklahoma, is I believe that we had some of the highest winds that we have measured since the network was established in 1994. So the perceptions of it being windy were spot on there. Another question, I would like to hear more about the OKET monitoring network. I'll toss this one over to Renee McPherson.
Yes. In Oklahoma, we have a 120 station network across the state called the Oklahoma Mesonet, and we measure a variety of both atmospheric and soil variables across the state. We do not directly measure evapotranspiration on that network, but we do measure the components, the variables that would, that using equations you can calculate the potential of evapotranspiration. And so I would encourage you, if you aren't familiar with the Oklahoma Mesonet and our products, that you can go to our webpage at www.mesonet.org, and I'll ask Margaret to type that in, and get the full list of products, and certainly contact our state climate office here, either me, Mark, or anybody else here at the state climate office who can talk to you about the products that we have available. One that may be of significant interest to those in the agriculture industry who are on the phone right now would be our soil moisture measurements. And we've, over the past week, we've had a substantial increase in soil moisture through the upper layer of the soil. Unfortunately, not down to 2 feet, but maybe down a foot in the soil in the western, about the western 2/3 of the state. If you flip off the panhandle, which I know some people are really interested in what's going on in the panhandle, and unfortunately they didn't get the precipitation. That's another product that we have on that network.
You had another question is, will the slides be available? And yes, we do post these. We'll post a PDF of all these slides on the drought portal in the NIDIS drought portal in the Southern Plains section. You can get there either from the link that's on the screen. The second link there goes directly to it, or you could just go to drought.gov, and in the upper left corner of that page, there's some drop-down menus. You can click Southern Plains, and you can get this. We're also producing a 2-page PDF summary from this. It took us a while to get that first one out. This one we should have out by early next week, and I'll work with the presenters today to get this summarized and posted there promptly, as well as sent out to those who maybe can join us today. So I think we have a couple more questions coming. Let's see, can we input drought impact reports for other folks? The answer on that is yes. We've been doing that, helping with Arkansas, is we set up a general email in this region, and I encourage really anyone on the call to use this. The best thing is to go to the drought impact reporter and put it in yourself, because then you know you're conveying exactly what you want the message to be. But if it's easier to send an email or something, you can just email us either with a skip site, or we have a group email called drought@mesonet.org. You might put that up. That's what we've been using. If I know that there's a lot of county offices that are very busy and they don't have time to mess with new forms and stuff, it's easy to send an email. Just send us an email, and we will make sure it gets into the drought monitor reporter, as well as we'll copy it to your state climatologist. So any way that is comfortable for you sending them in, please do so. So I think that's probably all the questions we have. I apologize for running long today. I hope that this was a good summary of of La Nina and where we're looking at both the coming season and the longer term. We'll look through the results of the poll and find our discussion topic for next time, and I hope that you'll all be able to join us again on our next one, which will be on October 27th. So thank you, everybody, and have a good remainder of the week.
Thank you. Thank you, Mark.
Thanks.